Thermodynamics is a jealous god. It demands that you never get more out than you put in, that entropy always wins, and that there is no such thing as a free lunch. But in the twisted geometry of general relativity, there is a loophole, a glitch in the accounting software of the universe that allows us to steal from the most miserly objects in existence. We are talking about black holes, specifically rotating black holes. To the uninitiated, a black hole is the ultimate sink, a cosmic dead end where matter and light go to die. But this is only true for the event horizon itself, the point of no return. Before you reach that dark threshold, you encounter a region that defies intuition, a place where space-time itself is being dragged around the singularity so violently that standing still is physically impossible. This is the ergosphere. In this churning maelstrom, the fabric of space is moving faster than light relative to the stationary universe outside. It is here that the laws of conservation we cherish on Earth begin to fray. In the late 1960s, the physicist Roger Penrose realized that this region offered a unique opportunity. He proposed a thought experiment that shattered the concept of the black hole as a mere consumer of energy. Imagine you're a sufficiently advanced civilization, hovering safely outside the ergosphere. You take a piece of matter, call it a fuel tank or just a rock, and you toss it into that swirling current. But you don't just let it fall. At a precise moment, you trigger a separation. You split the object in two. One half is kicked against the rotation, plunging through the event horizon and into the singularity. The other half is kicked forward, escaping the ergosphere and flying back out to you. If you do the math, something impossible happens. The fragment that returns to you has more energy than the original object you threw in. This isn't alchemy, it is a transfer of momentum. The half that fell in effectively had negative energy relative to the outside world. By swallowing it, the black hole lost a tiny fraction of its mass and rotational speed. You haven't created energy from nothing. You have braked the black hole. You have turned a collapsing star into a battery. This mechanism, known as the Penrose process, proves that a rotating black hole is not just a grave, but a flywheel. It stores an astronomical amount of energy in its spin, enough to power a galactic civilization for eons. However, the Penrose process as originally conceived is mechanical and clumsy. Throwing rocks into a blender is not an efficient way to generate power. You need perfect trajectories and precise timing, and the yield, while impressive, is limited by the mechanics of the brake. To truly hack the universe, to scale this up from a curiosity to an engine of infinite potential, we need to abandon solid matter. We need to stop thinking in terms of particles and start thinking in terms of waves. Because while a rock can only steal a discrete chunk of energy, a wave can do something far more terrifying. A wave can synchronize. From the mechanical limitations of the Penrose process, we graduate to the terrifying efficiency of wave dynamics. The shift from matter to radiation changes the game entirely because waves can overlap, interfere, and most importantly, amplify. This brings us to the concept of superradiant scattering, the phenomenon that turns a black hole from a passive battery into an active amplifier. When an electromagnetic wave, light, radio, or even gravitational waves brushes against a spinning black hole's ergosphere, it doesn't just bounce off. If the wave strikes at the correct angle and frequency, it interacts with the twisted spacetime in a way that allows it to steal rotational energy. The wave that scatters away is louder, brighter, and more energetic than the wave that went in. In the open universe, this amplified wave would simply dissipate into the void, a brief flash of stolen glory lost to the darkness. But what if we refuse to let it escape? This is where we build the bomb. Imagine constructing a megastructure, a perfect spherical mirror completely enclosing the black hole. This is the mirror trap. Now we introduce a single pulse of light inside this shell. The pulse travels to the black hole, grazes the ergosphere, undergoes superradiant scattering, and gains energy. It reflects off the mirror, preserving that gain, and heads back to the black hole. It hits the ergosphere again. It steals more energy. It amplifies again. This is not a linear addition of power. It is an exponential runaway feedback loop. The wave bounces back and forth, extracting spin from the black hole with each pass, growing in intensity until the energy density inside the mirror becomes unfathomable. The electromagnetic field inside the shell effectively becomes a photon bomb. We have created a system where the black hole's own rotation is being weaponized against it, converted into pure radiation pressure that pushes against our mirror containment. For a civilization, this setup offers two outcomes. The first is the ultimate power source. We put windows in the mirror, carefully bleeding off this super-amplified light to run our starships and megacities, tapping the black hole until it stops spinning entirely. The second outcome is catastrophic failure. If the mirror cannot contain the pressure, or if the feedback loop grows too fast to control, the shell shatters. The stored energy, potentially a significant percentage of the black hole's total mass energy, is released in a single instant. This explosion would act like a black hole bomb, a hard radiation that dwarfs supernovas, sterilizing any star system unfortunate enough to be nearby. It is a sobering realization. The most efficient engine in the laws of physics is also, by definition, the largest bomb the universe permits us to build.